Hello, everyone. This is Volts for September 5th, 2025. How inverters can stabilize a renewables-heavy grid. I'm your host, David Roberts. If you have paid any attention to power grids at all, you've probably heard the following. The reason modern electricity grids are such a miraculous achievement is that they have to remain in perfect balance at all times. The amount of electricity entering the grid must precisely match the amount leaving, or else frequency fluctuates, problems cascade, and eventually there are blackouts. You may have heard this fact and thought, well, that can't literally be true, can it? It can't be the case that every time I turn on my stove, some power plant operator turns up the output of their power plant by a stove's amount at that exact second. That's fantastical. There must be some buffer. And you're right, there is. In the seconds or milliseconds between when demand rises or falls on a grid and a grid operator is able to respond by adding or subtracting supply, the energy to buffer that transition and keep frequency and voltage under control is provided by inertia. Specifically, almost every electricity generator involves a large spinning mass, rotating coils through a magnetic field. And there is kinetic energy in that spinning mass, like a flywheel. That inertial energy can be tweaked very quickly. The mass can spin more quickly, thereby absorbing energy, or spin more slowly, thereby releasing energy, keeping the grid in balance in those key seconds. Collectively, spinning masses constitute a kind of shock absorber for the grid. Now, here's the first twist. Solar panels, batteries, and most wind turbines, the building blocks of tomorrow's energy system, do not connect to the grid via large spinning masses. Rather, they connect through inverters, which are all electronics, no moving parts, nothing spinning, no kinetic energy. Lacking inertia, inverter-based resources have not, to date, actively contributed to grid stability. In fact, there are widespread worries that replacing primarily fossil fuel-based spinning masses with clean inverter-based resources will leave grids with too little inertia, too little buffer, prone to accidents and breakdowns like what happened in Spain and Portugal recently. But here's the second twist. A modern inverter, properly programmed, can effectively mimic a spinning mass, adding or subtracting tiny increments of energy to the grid in milliseconds. This ersatz spinning mass provides what is called, in the business, synthetic inertia. Inverters attached to batteries are best at this for reasons we'll get into, but inverters on solar panels and wind turbines can contribute as well. So, the problem is solved and we can all go home? Haha, of course not. It is never that simple. To get into the details, I have with me today two experts. Daniel Duckwitz works on grid stability products for SMA Solar Technology, a large power conversion company based in Germany. Catarina Augusto is a renewable energy engineer who works on grids and flexibility for the nonprofit Solar Power Europe. As you could probably tell from the lengthier than usual intro, this subject can get somewhat technical. But the larger issue we're circling around here could not be more simple and profoundly important. Can we or can we not run a stable electricity grid on renewable energy? All right then, with no further ado, Daniel Duckwitz, Catarina Augusto, welcome to Volts. Thank you so much for coming.
Thank you for having us.
Very excited to get into this. I think this is a technical area that is hugely important and I think largely invisible to a lot of people. So I'm excited to get into it. I want to start, Daniel, with you. Just for people who are not familiar with this area and this stuff, I touched on it in the introduction, but these spinning masses, maybe you could just briefly describe what services they are providing to the grid, the kind of services that we are going to have to get from somewhere else if we retire these spinning masses. What are sort of the main categories of services they provide?
Yeah, so I think your introduction was really, really good. So turning on the stuff is probably not the reference scenario for planning the security of supply of a larger interconnection, but instead it would be scenarios like a sudden loss of a really large generator, like a gigawatt scale power plant, or like a transmission failure that suddenly disconnects a really, really large load center. And in these cases, it's not, sorry to say that, as insignificant as your stuff to the power system.
Right.
But it is really getting the system into trouble. And what happens if there is such a sudden unbalance is that this instantly missing power will be taken from the rotational masses, from the energy of these flywheels in the synchronous generators. And this will buffer the system so that the operators of the power system, but also of the individual power plants, they have time to adjust the output of their plants, or an automatic control system in the plants can adjust automatically the output.
And can you say just quickly, how long is that interval between sort of a big event, say some other power plant trips off, there's a big hole in supply, the grid operators are going to respond by turning some other power plant up. How long does that take? Is that milliseconds? Is that seconds? 30 seconds? What's the range?
It would take around 1 to 30 seconds to adjust the output of the other plants. So they would use frequency control to detect that frequency in the system is falling or rising, and then they would automatically adjust. And there is a service, it's frequency containment reserve or fast frequency response services. There are different names for it, but they all do the same. They measure frequency in the power system, and then they increase or decrease the output of a power plant or of a battery. And in that way, they help the system to find back to a balanced state. But that is what happens after 1 second, 5 seconds, even up to 30 seconds. And then for the grid to get to that balanced state again, what it needs is some instant buffer. And that would be the power from the inertia and the energy from the inertia that will be instantly available within less than a few milliseconds. And then up to the point where the power plants can adjust their output according to the needs. And that is the role of the inertia.
When we talk about these services, these grid services, there's inertia. Is frequency control separate from that somehow? Is voltage control separate from that? Are there distinct services here, or is there just the one? Injecting?
Yeah, there are active power-related services that aim at balancing frequency. And to have frequency in balance, you need generation and load in balance. That is the one, let's say, one part of the grid services world where traditional frequency control services would be part of. The inertia is also part of that, but in the past, it has always been a byproduct of the rotating machines. Now it will be a service that needs to be defined regarding how much power, how much energy should be reserved from the batteries, and how fast and in what relation to others should they have the reaction. So this would be the frequency control, active power related services. And then on the other hand, there are voltage related services which balance the voltage in the grid to make sure that the voltage is very, very close to the nominal voltage in all locations.
And that is also provided by the spinning masses?
It can be provided by synchronous generators, it can be provided by statcoms, it can be provided by big capacitors or inductors in the system, and of course also by renewable power plants. So when we talk about voltage control services, it's once again a bit similar. You have instant imbalance that needs to be balanced. So that would be some inherent reaction or a very fast control scheme. And then there is more the steady state balancing of the grid. So to say, to balance within 5 minutes, to readjust the voltages to get closer to nominal again after some event. And this is like similar to the frequency and active power, but it is usually treated as two separate categories. And also the stability, there is voltage stability and there is frequency stability. And there are, in some big real-world events, they can also interact, voltage and frequency stability. But in the theory, in the textbook, it is separated.
Got it. And all of these services are at their root small injections or withdrawals of energy from the grid, right? I mean, that's whether you're talking about frequency control or inertia.
Yes.
One way or another, you're talking about something very quickly injecting or removing energy from the grid.
Yes, exactly.
This problem of low inertia leading to problems, is that a purely modern problem? Is that something that's new to us with the retirement of fossil fuel plants, or do we have historical experience with low inertia on grids?
It is now, at the moment, we are dealing with a specific transition where rotating machines are being removed. But also in the past, there have been events where low inertia power systems were operated, and that is systems that focus on hydro energy, because the turbines in hydro, they have a higher power density because the water will have a higher power density compared to steam.
Right.
And that means the turbine has less mass, less inertia. And let's say the power systems that have focused on hydro, like parts of Canada, maybe parts of the US, for example, Norway, they always had, let's say, their engineering to do regarding frequency control. But of course, today we're talking about something different compared to these, let's say, older versions of the engineering problem.
So in terms of just a bunch of spinning masses disappearing from the grid and us needing to compensate for that, this is a new thing that's confronting us, basically.
Yeah, I mean, the big difference is that today solar plants, but also wind plants, they are interfaced through power electronic converters to the grid, and these don't have any rotating mass. So it's not like they have low inertia, but they have no inertia. And that is a new quality, of course, but also something that can be solved as an engineering problem. Yeah.
Right. I mean, when it finally sank into me that all these different grid services we're talking about are some version of injecting or withdrawing energy from the grid, it sort of clicked to me, why wouldn't batteries be able to do that? I mean, it seems like batteries are much more purpose designed to do that than a giant spinning mass. Like if you, I'll just put it this way. If all you wanted was those services and you had a blank sheet of paper, you wouldn't build a giant spinning mass to provide it, right? I mean, it just seems like batteries are more natural in this role. It seems to me anyway. But so Daniel, an inverter, this piece of electronics, briefly describe the difference between sort of inverters to date traditionally have been what are called grid following inverters. And what we're discussing today, inverters that are taking an active role in shaping and stabilizing the grid, are called grid forming inverters. Maybe just briefly explain what's the difference there. What was a grid following inverter and what do grid forming inverters do that's different?
Yeah, so when connecting an inverter, the control system of that inverter needs to make sure that the current of the inverter is synchronous to the grid voltage, so that it will have the right AC waveform, so that it has the right synchronous waveform to feed the power to the grid. Mm-hmm. And to do that, the grid following inverters, what they do is they observe the voltage. They also calculate the frequency based on the observed voltage. And then they follow the grid with their current. So they are basically observing what is happening out there and then synchronize according to what they observed.
Right. So they match the grid's conditions.
Yes, they match it, and then they can feed power. But then when it comes to the inertia, we discussed it has to be activated within milliseconds, or it's not really, it doesn't have to be activated, but it has to be provided within a millisecond. maybe even without the inverter noticing that it is already providing the response. And that is the difference. Instead of observing the grid and following the external frequency in the grid, these grid forming control schemes, they make the frequency and they make the voltage. And that means that if you switch on your stove or anything larger happens out there, the voltage will remain a stiff voltage source, and then the current needed by your stove will just begin to flow according to the needs. And that in turn will then have an impact on the frequency that the grid forming inverter makes, or the internal state of frequency that it has in its control system. So that's the fundamental difference. It's not observing and following, but it is making it. And if it notices there is some higher load, it will adjust its internal frequency. And that is the fundamental difference between grid following and grid forming.
Right. So maybe like a good way to think about this is active versus passive. Grid following inverters are just sort of passively matching grid conditions, whereas grid forming inverters are purposefully shaping them. Now, let me ask this, and this is also something that I've had a time wrapping my mind around. The difference between a grid following inverter and a grid forming inverter, is there a physical difference or is it just software?
I mean, to make the fundamental shift in principle of control, the hardware doesn't need to change. But then once you look closer, what is the actual stability need of the power system? You can adapt the design of the inverters to be optimized for applications with inertia. Like, for example, to have a defined power and energy reserve built in to the battery system and the inverter to really have the reserve for your stove or for some larger incident. Yeah. So maybe I'll stop using the stove example, but if you think about a loss of a large generator, like maybe a 3 gigawatt power plant, that is a few percent of the overall system generation and the overall load. So you need a significant amount of power reserve in these inverters to really provide this additional power and energy instantly. And that is where design adaptations come into play. But then the very fundamental difference is not in hardware.
I see. But there is some difference in hardware, because what I've been wondering is, could you just go to an existing old-fashioned inverter and update the software on it and make it grid following? Or do you have to purpose build it to be grid following from the beginning?
It is possible to change the operation in the field. So it can be done.
Really?
Yeah, it can be done. But then once you start thinking about what you want to achieve, often you come to the conclusion that the benefits are not as big as if you build a new one. And then also when we look at how much battery storage is being built at the moment and how much has been built like 5 years ago, it makes sense to consider it, but then it also makes sense to focus on the new projects and really design them in the first place for providing inertia with a defined performance. This is, let's say, we can go both ways, but
I'll tell you why I'm asking, because all these things are connected to the internet in some way or another. And if this is software controlled, shouldn't you be able to update the software over the internet? And if that's the case, that's basically free. I mean, not free, but like,
yeah, it's
cheap. Like, so if you could just over the air update all existing inverters to have new software that allows them to be grid forming, why wouldn't you just do that? Like, why not make them all grid forming, I guess is what I'm asking.
Yeah, it's a good question. Yeah. And also a good idea. No, really. We should really not forget that it can be retrofitted. But then, it's not like we can dial into the larger battery storage plants and just install a new firmware. So,
I'm sure it's not simple, but but there's no moving parts, right? It's pretty cheap to do it if you can arrange it.
Yeah, there is one part that you would basically have to renew the grid connection approval. So you would do, let's say, all the engineering that you have done regarding grid connection, grid code compliance, that you would repeat for doing the retrofit to get the permission from the network operator to do it. It is feasible, and we have done it. Yeah? So it is not impossible.
I mean, I guess from a network operator's perspective, though, a grid forming inverter is always going to play better with the rest of the grid than a grid following inverter, isn't it? I mean, it's always an upgrade from a grid operator's perspective, isn't it? It's just more intelligence out there to make use of.
Yeah, there are also some concerns, like losing control over the transmission network or of the distribution network. That is because the grid forming inverters, they would allow the system to keep operating autonomously without all the other stuff that is needed today, like rotating machines. So usually when all the rotating machines are shut down, that's not happening in real world, but for maintenance works in the grid, for example, the network operator and their service personnel, they really, really want to be sure it is shut down if they isolate it. But with grid forming, it could actually continue to operate. And then there is a safety concern. Yeah. And I mean, it sounds weird when you hear it first, but then on the other hand, it's really about the safety of the lives of the personnel out there that operate the switches and build the equipment for the networks. And this has to be ensured. And that is why it's not like, usually let's say the high level transmission operator staff, they want it. They want it really, really quickly.
Oh, yeah. Because it just gives them more control over pretty straightforwardly gives them more control over their network, doesn't it?
Yeah.
So let me ask this. Mostly what we're talking about here, I think, are inverters on batteries. So like an inverter on a battery could set aside, 1% of the battery's power in a little reserve that you could set aside for these grid faults or grid events when you need a little reserve power to bridge that millisecond gap that we're talking about. What about inverters on solar panels and wind turbines? They can't store power, obviously. Can they, though, offer other grid services?
Yeah.
Like, do they count as grid forming if they're attached to a solar panel?
It is hard, to get grid forming with active power-based inertia with a solar panel because there is no storage neither in the panel nor in the inverter. So this wouldn't be possible at the same level of quality like for a battery. But then what the PV can do is really, really quickly reduce the power, because for reducing, you don't need storage. And it can also instantly or almost instantly balance the voltage, which would be the reactive power part of the services. But then for really providing inertia that is reliable and has a defined performance is really, really hard with solar plants.
Right. So grid forming inverters on solar panels and wind turbines can offer some services.
The thing is, we would probably not call them grid forming, but this would be some advanced
inverters?
Yeah.
Inverters plus?
We call it transient voltage control for PV inverters. That means they will behave like a voltage source, but only regarding reactive power and not regarding inertia. So there is some middle ground between grid following and grid forming, and this would be what a PV-only plant can do. But then there is also another trend, and that is hybrid plants, which means many, many plants have a battery and solar. And even for wind, there is a tendency to do more batteries combined with wind. So there is options.
Right. So you can do some with inverters on wind turbines and solar panels, but to be fully grid forming the way we're talking about, to really substitute for spinning masses, we're talking about batteries here for the most part.
Yeah.
Are there things that grid forming inverters can do for the grid that spinning masses cannot do? Are we getting anything extra here with this substitution?
There are some advantages, because you can program the behavior, and for the synchronous machines with their turbines, there is a tendency for oscillations between the turbines and the generator and the grid. There can be oscillations, and then you need additional damping controllers in the power plants, and these can only be tuned to be so good. But then when you do it as an emulation, you can tune the control system to avoid these oscillations in the first place, to provide damping for existing oscillations between other generators in the system. So this is a degree of freedom that conventional power plants don't have. And then there is another advantage, and that is for a thermal power plant, to adjust the output, you would have to adjust the amount of steam or the amount of fuel that you put into the turbine. And this takes some time. And that is why frequency control services, according to, let's say, the synchronous machine-based world, these will have response times in 10 to 30 seconds, which is absolutely not necessary for a battery. The battery can adjust its steady state output within half a second. So there are options to improve the overall system behavior to get back to the steady state much more quickly than before.
I see. So in some ways, these inverters do what spinning masses do better than the spinning masses do it.
Yeah, they can do better. I mean, we are working with existing systems, and an existing system will have varying amounts of rotating generators in it. So if it's a sunny day, there will be almost no rotating machines. If it's a cloudy day, there will be some, and at night, and if there is wind and there is no wind. So we're dealing really with percentages of rotating machines versus inverters in the range of 10 to 100%, I would say, which means you can do better with the batteries, but still you need to be compatible with the old system, which means you shouldn't be too different.
One of the things you mentioned when we were exchanging emails beforehand is that one of the things maybe that batteries with inverters can do that spinning masses can't do has to do with sort of bolstering weak areas of the grid. Can you talk just briefly what you mean by that?
Yeah, when we talk about weak areas, that is usually coming up in an area that has a lot of land, a lot of renewables will be built, but there is not much else, no loads, and also not a lot of other generation. So in Australia, this happens.
Yeah.
I'm sure there are areas in the US, in California, in Texas, all around probably, where there are these really, really high renewable generation areas. I mean, you wouldn't build as a system operator, ISO utility, you wouldn't build any more transmission lines than you absolutely need to build to feed the power.
We don't even build the transmission lines that we do need.
Yeah. I mean, yeah. So you will operate the transmission line really very close to the limits, and that means it will become a weak grid area. That means the voltages has a tendency to not be very stable, not be very firm. And this is where the grid forming will improve the voltage stability a lot. And that is actually what is happening in these systems. For example, in Australia, there is a system strength assessment framework. So if you want to connect in such a grid area, you have to find a way to either reinforce or to make the voltage stronger by, for example, building a grid-forming battery instead of a grid-following one.
Interesting.
Or you would have to pay a fee to the system operator, and the system operator will then use that money to do something else to reinforce the system.
Well, I think people, especially listeners of this pod, are familiar with the interconnection process where you sort of apply, I want to join this grid, then the ISO assesses the grid and decides whether you can join on. And one of the big things that's slowing things down here is your power plant might be the one that triggers the need for additional infrastructure.
Yeah.
And if that additional infrastructure is transmission, that's a huge increment of cost. But if you could put a battery with a grid forming inverter as an alternative to building new transmission, that's much, much cheaper and faster, is it not?
Yeah, sure. And that's the approach.
So this could speed up interconnection, in other words, is the point.
Grid forming is the key to speed up interconnections within some boundaries, of course, because you still want to transport the power from there to there, and you need a transmission line for that. But it is really, really the big and quick win for speeding up the connection process. Yeah.
Interesting. Okay, I got one more technical question, and then I want to talk to you, Catarina, about some policy questions. But just so listeners can wrap their head around this, what is the scale here? Like, how much grid forming battery would we need to replace all or the vast majority of spinning masses. Like, is that a reasonable, realistic thing to think that there are enough batteries to do that?
I think we are, not halfway there, but I think the amount of batteries that is needed for operating a system independent of the generation mix so that it can work with any generation mix, it would be around the same installed capacity or installed power of the peak load of the system. And then you can operate it completely without any spinning masses. And you would have all the reserves you need. And on the way there, I think even having half the peak load installed as batteries is already really a big step. And in some power systems, I think we are getting close to that point where half the peak load is already installed as storage.
There are grids in the world now where this has penetrated to the point where it's, these problems are present day problems in some places, not in the US yet. So Catarina, let me turn to you then. From a policymaker's perspective, how much of this is out in the field? How much do we know about the performance of these things in the field? Do we know enough that policymakers are familiar with this, confident in it? Do they know about it at all yet? Where's the sort of like policymakers' level of familiarity with this option? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts, people using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Do they know about it at all yet? Where's the sort of like policymakers' level of familiarity with this option?
So in terms of familiarity, there's already a lot of, especially with the situation of the blackout now, I think grid farming become more popular than grid investments.
Right.
Everyone's speaking about grid farming and everyone got an expert on grid farming. That's what I feel. I was listening very attentive to Daniel, and I'm always learning with our technical members, giving all the insights. And I feel that's the problem. So it's already there. So there is one thing that all the grids need. It's a set of rules, so requirements to connect to the grids. And these requirements are, let's say, the base rules that you need to fulfill to be able to maintain the stability. And the current ones in EU already include grid farming as part of this. They don't really define grid farming, so that's the problem what Daniel said. If PV as a standalone, it's part of it or not?
Yeah, well, does it? I mean, if I'm a PV plant and I don't have a battery, but I do have smart inverters, can I then satisfy that requirement? Can I call it a grid forming inverter legally?
Yeah, so legally, it seems that's going on that direction, but it's not the reality. And that's what the industry is trying to clarify. So I think that's the part, the knowledge that's not really clear.
Interesting.
Not just for the policymakers, but I think also for the system operators, because in the end of the day, when it comes to sustainability, policymakers will look at transmission system operators, at distribution, and ask, especially to transmission, what you need. And they will say, well, I need more grid forming. So I need that now renewables know how to answer to grid forming. And that's the part that Daniel explained very well, that we need to have a bit of clarity. What is grid farming coming from batteries, and what is the stability services that renewables, when they don't have batteries, can do?
So just to clarify what you're saying, interconnection rules in place in EU already have something about grid forming in them. It's just not super clear what it means.
Exactly. So they are at the moment in a revision of the European Commission. So there is a process. It usually starts with a regulator where it kind of assess, because these codes already existed. So you need to kind of assess what kind of changes you need from time to time. Usually it's around 10 years. So let's say if we mess up now, we have to wait 10 years to correct them.
Yeah, right.
And now it's on the commission, and it's at standby, what is also a concern, because it's not really progressing, and we need to look at requirements for stability, and we need to put the right technologies entering to it. So that's a bit of a concern now that it's on a standby.
So is one of the possibilities here that you could imagine interconnection rules that just say, no matter what kind of generator you are, you also have to have a battery with a grid forming inverter attached to it, right? I mean, you could imagine just because, like relative to the cost of a power plant, I can't imagine a few batteries and a grid forming inverter would be that much more expensive. Like, is that in the realm of possibility that just everyone could be required to do this?
So ideally, yes. And let's say the strength of, so Daniel said about hybrid systems, so connecting PV or wind with any other energy, in this case would be with storage. It's something that we are seeing more and more. And I think it's also something that you want to do it by yourself without any kind of rule, because you already want to optimize the way you use that connection point.
Sure.
It's gonna be better for your business.
Why not do it? I was sort of wondering along those lines, like if I'm a natural gas plant, I could stick a battery next to the plant and put a grid forming inverter on it, and then I could be a grid forming natural gas plant, couldn't I? I mean, is that something anyone's trying to do?
I think a gas plant doesn't need the battery, but maybe Daniel can correct me on that. But yes, you can.
Well, if it's a requirement, if it becomes a requirement, maybe they'll have to.
For bigger plants will be. So what happened now is that the requirement is mostly for transmission system
I see.
parts. Everything is distribution. They are allowed to design a kind of a roadmap. So how they see progressing the need of grid forming at distribution level. But the request for now, it's at transmission level. So every kind of plant on transmission level will need to be capable of providing grid forming. And from a certain more higher value, we will need to be able to give inertia. So there, the storage is already implicit that you have to add storage to a PV power plant.
In terms of policy, in terms of how you encourage this, I mean, it is somewhat of an extra expense. So I'm wondering, are there markets in place? Like in the US, we have these ancillary service markets where people can get paid for voltage stability and stuff like that. Are there markets to compensate grid forming inverters for the services they're providing to grids?
Yeah, so that's the big problem of hybridizing PV plants. It's that there is not sufficient revenues for storage in general. And when it comes to stability services, when we speak about grid forming inertia, there's nothing there. There's a requirement that you need to have, but nobody's going to tell you how they're going to be activated or procured. And that's the law missing, is that we're looking at flexibility services. We are looking into expanding that section of storage. But then when it comes to stability, that's another field. There is no really a market for that. So we are not at the same level as UK, and that is a bit closer to us, where they have grid forming pretty clear already for some years on market.
Can we talk about that for a minute? I wanted to ask about sort of markets that are ahead on this or doing better on this. And the UK is an example that gets brought up frequently. So what's the UK situation with grid forming inverters?
So UK, they also have the situation where they have rules, requirements that need to be designed by law when it comes more technical understanding, how you proceed and how you define grid forming. And then they have a market. So it means that you procure through market. So you need to comply if you have grid forming. So you are not obliged to have it, but if you have it and you want to provide that service, you need to comply with certain requirements, and then you can provide it through a market. So that's the difference of two realities. So let's say they're more forward-looking on a sustainable development of storage and grid forming, Because that's also another concern, is that if you don't have a market, you are not really reacting to needs. So you said before, and what about if we turn all the storage into grid forming? I don't think people really know of the impact that will bring to it, and if there is really the need of these services for all storage. So what Daniel also said in the beginning, maybe we don't need to retrofit the existing plants with grid forming inverters, and we can continue with grid falling. So that's another concern.
One great advantage of markets is that they reveal that information.
Exactly.
They reveal how much do you need, how much is it worth to do this, and that kind of thing. So is it the case now that every battery that's being installed in the UK has grid forming inverters on it, and they are active and working on the UK grid?
I'm not saying maybe every battery, to be honest, I don't know, because as a developer of a power plant, PV plus battery, you need to decide what is your ideal business case, and maybe not everywhere it makes sense.
Right.
Yeah, maybe to add on that. So what we see in the UK is there is a market for inertia services, and basically everyone at least is evaluating if they can participate, and they need to do some technical qualification process with their plant. And then often the grid connection is not available within the next 5 years. So there are a lot of other obstacles for developing a storage asset. But then recently what we see is that really most of the batteries will be grid forming ready in UK, and also the developers prepare them from the technical design perspective for providing the service with a high amount of inertia later. So basically, if there is a market, the more inertia, power and energy the BESS can deliver, the more revenue it will make. So there is an incentive to optimize the design for having more performance available. And this is something that is good if you need a lot of inertia. It's good to have the batteries optimized to do as much as they can. And then also in contrast to, they are forced to do it, but then everyone would try to keep the extra cost as low as possible and probably not deliver the highest quality of the service.
Actually, this gets back to a slightly technical question, which is, if I'm a battery and I'm in a particular region and I want a grid forming inverter, to what extent is that grid forming inverter just something I buy off the shelf versus something that has to be specifically programmed based on the conditions in the region where I'm located? How bespoke, I guess, is a grid forming inverter?
So when it comes to requirements, there is a set of requirements that you need to comply with to have that certification later. So at the moment, if you don't have this European set of rules, it may happen that in you will have 27 versions at least of inverters if you have one TSO per country. And if we go to this distribution level, you may have more.
Right.
So that's a problem. But I don't know if you want to add something, Daniel, in terms of more details on the technical requirements.
Yeah, I think basically what we can tune for, I mean, not for the individual inverter necessarily, but for the overall BESS plant, is the amount of inertia it can provide regarding power and energy. Also the amount of short circuit current, which would be the short-term voltage support amount. And this can be tuned. It also reflects to the hardware design, but then there are also some country-specific parameters. But what we would aim for is, as an OEM and engineering partner for our customers, is that we are not starting from scratch in every market, and especially not in every state of the European Union or every state in the US, but that we have a defined standard, probably one for Europe, one for US, one for Australia,
right.
And then we only do minor adjustments depending on the location. That would be an ideal target, and also we do aim for getting as close as possible to that situation, because it is just more efficient and we have a lot of work to do anyways. Yeah.
What about Australia? Is there something interesting to say about what Australia is doing here? Because Australia is really far down the road on renewables. I guess their goal is 82% renewables. I don't know where they came up with that number, and are getting close and regularly have periods where 100% or more than 100% of their energy is coming from renewables. So it seems like if anybody's under the gun, and really needs to solve this problem is Australia. How are they ahead on grid forming inverters?
They do have system strength assessment framework. So they basically have an incentive, even though it's not like you add revenues if you do grid farming, but you avoid to pay a fee, or you could also say you avoid paying a penalty if you want. Yeah? So there is an incentive for installing grid farming already, but it's not very standardized yet. And also the defined quantities of how much inertia is required in which region, this is not, let's say it is addressed, but it will be addressed probably even more accurately in the future. And this is something that is it really helps to speed up the installation and also this stability transition if you define the target amounts of inertia, target amounts of short circuit level for each region or each larger state. That really helps to know where do you aim for and not just say we need grid forming, because that could mean a lot of different things, and it doesn't mean that you know what to do.
Well, again, that would be a great role for a market to play, right? Like the whole point of markets is kind of to define those things and give you a sense of those things.
Yeah, I believe we still lack transparency on the grid needs when it comes to now, for example, in Europe, it's mandatory for you to do flexibility assessments on grids and to make that part of the network planning. I think maybe we are missing something like this for when it comes to inertia and stability. It's not really clear. When you asked before how much grid farming we can substitute with batteries, we don't even know how much grid farming we needed at a moment and how it's going to grow progressively.
That seems a little crazy to me that grid operators are not regularly assessing.
I think they're assessing, but there's not really. If I asked, I never receive an answer.
I see. So they're treating the information as proprietary. One question I'd like to ask both of you is, what policies would you like to see here? Like, I don't know if we have enough experience with these things to do any sort of comparative, like what policies work and what don't, but sort of like what are the policy instruments here that could speed up the sort of standardizing and spread of the market for these things?
So first of all, the clear understanding what is grid farming and the recognition of TRL of technologies. I think that's not yet there. So there's a need policy on piloting, also experimenting a bit and gaining the trust of system operators regarding storage. And then I think this network code, what we call it here, the rules to comply with the grid need to have more harmonization for just the purpose that also Daniel met. And despite the fact that you have this clarity at European level on requirements, then you need a market to support the deployment of these services. Otherwise, you will not be able to maintain systems sustainable and for storage to grow. So I think this is the main key areas.
And is a EU-wide market for those services, is that on the table? Is that something people are talking about? Is there a bill? Is there a discussion at the EU level about this?
Yeah, there is now a demand response, what we call it demand response network code. So it's a market code. So it's the code that then stipulates how services are procured and which kind of services. And some time ago, now so the Commission now is assessing this code at the same time. And there was this question in the air from the regulation also, should we open this market from just flexibility to stability and bring the discussion of inertia? And I think that could be the place also. So take the chance that we are already working on flexibility services and start doing the same for stability.
Yeah.
How about you, Daniel? Are there particular policies that you advocate for?
I think, the UK approach, I do like it a lot, because what the UK has done is they have given a technical specification in their grid code. So there is a clear understanding of what is grid farming doing, how do I quantify inertia, what tests have to be passed, and so on. So the connection process is really well defined, and also the performance metrics are in the grid code. But then you decide how much of the quantity do you want to provide, which can also relate to the capex of your project. For example, if you want to overbuild the batteries a bit more or something. And then you decide based on the market, how much do you actually provide? And This is a really good approach of the technical specification in a, let's say, rule for a wider area like UK, and then also the market design. And Europe could just do the same like UK, because in principle, the regulation in Europe says there should be a market for inertia if it is efficient. And then so far, only Germany came to the conclusion that it would be efficient, and they are starting such a market next year. So I think we do have these options of doing it similar to UK. I think Australia also has the inertia shortfall declaration part, where they declare a lack of inertia in a certain area and then tender for filling up the levels that are missing. And for US, I can see some technical specification drafts, but there is no market incentive as of now, as far as I know. But we'd love to do a demonstration project in US, of course.
Catarina, maybe this is a question for you, but on the politics, one thing I think I don't totally have my head wrapped around, like this grid forming seems like an obviously good thing. It seems obviously good for the grid operators, seems good for ratepayers. It seems like it's helpful to generators, helpful to everyone. Is there an organized opposition? Is anyone against this stuff? I guess, do you know what I mean? Like usually when you, in any market you can identify in the US, you can find someone who hates it and is trying to kill it. Like, is anyone opposing this, or is it just a matter of the slowness of trying to work it into regulation?
I think there's not really a opposition, at least from our industry. There's a concern of not having the market and the right remuneration for it, but there is not a position on that sense. But I don't know if the synchronous machines will be so happy if we we feed him the leverage to start.
Well, I'm sure they don't want to retire for
Yes,
for a lot of reasons.
But we have to work on decarbonization. So, what can we do regarding that? But regarding the technology and progressing on grid forming, I don't think there is a position. I think what is missing, it's the market and the knowledge when it comes to the right technology.
Well, sort of the inverse question then is there a particular industry that is lobbying for this? Like who is actually throwing money around and lobbying and pushing on this? Anyone? Or is it just something that wonks love? You know what I mean? Policy people love. Is there an actual industry that's committed to pushing this forward?
Yeah, I think the transmission system operator. And then, of course, it's a good service that storage can bring. So, of course, it's something that also storage industry is wanting to make it more clear. And that's why it's important also to understand the added value that they have. But I think it comes also as a request from the transmission system operator. There is just the need of a bit more, I understand, for the stability part, they need to be more conservative on the ideas and be cautious.
Yeah.
But at the same time, innovation is progressing a lot on storage. So I think that's the part that is still mismatching a bit.
Yeah, this is a fast-moving technology in a slow-moving industry. Well, Daniel, we're running out of time, but I just wanted to conclude by trying to press a little bit on this question. You know, a lot of times on this show, we cover clean energy, we cover the energy transition, and I get excited. I get excited about new things, new technologies, and new ways of doing things. But I don't want to inadvertently sort of oversell this. So I guess I just push a little bit on, are grid forming inverters at a level of technology readiness that actual technical nuts and bolts grid operators and utilities feel comfortable with them? Like, do we really know for a technical certainty that these can step in and do all the work spinning masses we're doing? And are we confident? Like, what is our general level of sort of industry and technical confidence in this?
Yeah, so personally, and also as a company, we are fully convinced that we can do this. But then,
well, you sell them. I mean, you'd have to be convinced,
yeah,
right?
Well, I mean, I could just argue for selling the grid following stuff, which is
that's true.
Yeah, but then no, we are really, really committed to not only selling the grid forming technology, but we are also committed to making the power systems of today and tomorrow stable. Because without stability, the energy transition is not going to happen. So this is really, really important. Also for our business, it's important to have stable systems. And this is why we also focus on this kind of technology. But then when I talk to transmission system operators, I think maybe 10 years ago, 15 years ago, when I had the first talks with TSOs about, it wasn't even called grid forming back then. It was virtual synchronous machine or whatever. and they were like, it doesn't work, does it? And I was like, well, I was in research back then, and I think it could work. Let's do some research. And then we did some research and so on. And I think nowadays, like I would say 8 out of 10 engineers in the transmission companies are convinced it is going to work. But then we need, of course, to convince the other 2. And the most important part is to really prove the technology in the field and do these demonstration projects, gain the experience even in an exchange. And it is sometimes really causing a lot of extra effort to do this, but then it is worth it, because only with proving the technology out there in the field, in demonstration projects, but also the first commercial projects are out there online, really gives the confidence to move onward and do the right thing.
I mean, there are grid forming inverters on the grid doing grid forming.
Yes.
Like it's not theoretical. It's out there happening. So there is performance in the field to assess here. We're not speculating.
So we are in UK, we provided support to the commissioning of the Black Hillock project, which is a 200 megawatt battery providing inertia to the system since February of this year.
And this is where again? Is this the one in Sweden?
It's in Scotland, in UK, Scotland.
Scotland.
And the location is called Black Hillock, but I guess a Scotsman would pronounce it completely differently. I don't know how they would say. But then Black Hillock, that's how I say it. And that's the first plant that is online since February. And in March, there was this trip of a large gigawatt scale power station, and it has already provided inertia in that scenario. So it has proven its contribution to stabilizing the system 1 month after commissioning. So this is really giving us some confidence in the real world performance. And it's not the only plant out there. We have also some smaller scale demonstration plants out there, which have also been operated for between years and several months. And they have also responded to grid events of that scale. And we can see it works. And we're really, really looking forward to doing this in more and more markets and countries.
I saw the little demonstration project in Germany where the one region islanded, cut itself off from the national grid and ran purely on renewables and grid forming batteries for, I don't know, like an hour or something.
Yeah.
It was like, I don't know how seriously to take that as a demonstration, but like, does seem like.
Yeah, it was back in 2019. It was the first demonstration of the feasibility on I think it was a 15 megawatt plant, and this small town was isolated from the transmission grid. So it was back then the first larger demonstration of the feasibility. But it was operated for an hour off grid and then resynchronized. And then since then, I think it is resynchronized. But there are other projects where we prove the technology every day. And the whole purpose is not to operate as a microgrid, but to operate as part of the interconnected system. And we're getting more and more experience with that kind of operation.
Right. And I didn't mention this before, though I guess I'll just throw it out now. But like SMA, your company, you guys kind of got started with these inverters on microgrids. So like these things are sort of grew out of how can we have an islanded microgrid freestanding, right, operating on its own. That's what sort of spurred the development of these things. And now the idea, I guess, is just to sort of like expand that out so that the macrogrid basically becomes.
Exactly. Yeah, so it started with a 5 kilowatt Sunny Island inverter, which has been operating in many remote areas for, I don't know what kind of energy supply situations, like a really, really small village out there where there is no distribution grid or no grid at all. And then they got a bit larger and larger, but then since around 10 years, we have been working on bringing this to the interconnected systems. And during the past 3 to 4 years, it has really gotten bigger. And we have now commissioned the first 100, 200 megawatt scale projects. And so it's really evolving since more than 20 years, from the very small units to the bigger units. But the aim was the same back then, to operate these microgrids without diesel genset, or to be able to operate them without diesel genset throughout the night in summer, but maybe not in winter at first, and then increase it. And that is really like a small energy transition. And now we're doing the big thing. I hope that we will all do it together now.
Yeah, it's moving so quickly. It's so interesting. Catarina, which grid do you think is going to get there first? Who's your, if you're betting on a horse, who do you think is going to get rid of their spinning masses?
The country, you mean?
Yeah, well, a region, I don't know, a grid, any grid.
It doesn't count UK, I imagine.
Well, if the UK could, I mean, they still have lots of gas, right? I mean, they are some gas. You think they're going to get closer first?
I wanted to say yes, but I don't know, because to be honest, Germany has a lot of solar deployed, but I also know that some policies are very still oriented on fossil fuels, so I'm a bit skeptical there. However, maybe this inertia market will do the job and make things go faster.
Well, let's hope so. Thank you two so much. This is super fascinating. Like I said at the beginning, it's technical, but this is like, if you're trying to get from a grid with some renewable energy on it to a renewable energy grid, this is a step you have to take. This is a technology we have to master. So thank you two for coming on and walking us through it. This is fascinating.
Thank you for the invite, David.
It was great. It was a pleasure.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.